Students, once again welcome to another video of iCampSA, where we are dealing with functions, traits and functions. And today the topic of focus is gonna be hyperbolic functions. If you remember, when we first introduced functions, we said functions are a graphical way, or functions can be either graphical, they can be form of an equation, or they can be in a table form, but the most common thing or the most basic characteristic of functions, that functions, they represent relationships between variables or between things. That is the whole point of a function, is that they represent relationships between things. And then here we are focused on graphing the functions, showing the sketches of the functions, and also working with the equation of these different functions. We've already dealt with linear functions and parabolic functions, and here we are dealing with hyperbolic functions. Hyperbolic function. Without wasting any time, let's get into hyperbolic functions. Okay, so as the other functions that we have covered so far, parabolic functions also has a matter graph, so it's the most simplest form of this function, if I may say, which is what we call the matter graph. And the equation for the matter graph of the hyperbolic functions is y is equal to 1 over x. That is the most basic equation, of the hyperbolic functions, and that is the equation that we use to sketch the matter graph function. So before we get started in this session, I want us to do something a little bit different. We'll start by sketching the function, the hyperbolic function, because there's something that I want you to see. So far we have been dealing with continuous function, but a hyperbolic function, when we sketch it, something interesting happens. There are some values that the function never touches. It will approach but never touches, and we call those asymptotes. But I think the best way for you to understand or to see what we mean by the asymptote is for us to sketch the hyperbola, to sketch the function. So just like we did when we were sketching the other function, let's start with our table. We'll select x values. That we'll input into that equation in order to find the y values. So the x values that we're going to go with, we'll start with -2, -1, 0, 1, 2. Just a few x values, and then let's go ahead and also find the corresponding y values for this equation. So we're going to say 1 over x, and we'll substitute the x values to find the corresponding y values. So we say 1 over -2, that will give us -1 over 2, so it's -half. And then for the second value for the y function, we say 1 over -1, of which would give us a -1. And then we go ahead and say for the third value, we'll say y is equal to 1 over 0. And look what is happening here. We are dividing by 0, and we can't divide by 0. When you punch this in your calculator, it will give you an error. So the function at that point is not defined. Maybe I'll just say we get an error there. So our function will exist for all the values that we have calculated so far, but when we get to 0, our function doesn't exist. So what happens? You will see what happens is that the function will actually jump. Okay, and then next let's do 1 over 1. 1 over 1 will be a +1, and then 1 over 2 will be just a half. Hopefully these values that we have selected here will be enough. Hopefully I think doing a little bit more or adding the values of x could have actually helped us could have actually helped us. But anyway, let's go ahead and sketch this function with these two values that we have selected, since we have already committed to this function. And then let's draw to these values. Let's draw our Cartesian plane. These are our y and x axes. We're gonna have 1, 2, 3 and 4. Okay, and then next we're gonna have 1, 2, 3 and 4, and then we're gonna have 1, 2, 3 and 4, 1, 2, 3 and 4. Okay, so we have those values. Okay, but before maybe we even get to sketching, let's also do something interesting. And see what happens, So at some point our function will have to let's just assume and try to see what happens when our function, where y is equal to 0. Let's try to find the corresponding value of y is equal to 0. See, we have that I want us to find the x value where y is equal to 0. Basically, I'm trying for us to find the x-intercepts where our function cuts the x-axis, So we have y is equal to 1 over x, and I want us to find the value of x where our y is 0 at this point, and that is actually an x-intercept. That is actually an x-intercept, as we have already introduced. So we substitute y is equal to 0. This is equal to 1 over x, and you see, when we are trying to solve for x here, we can't essentially solve for x because x multiplied by 0 would give us 0. So this is sort of undefined, Once again, it's undefined. So what does this tells us now? This tells us that also our function doesn't exist where y is equal to 0. So at that point where y is equal to 0, the function doesn't exist, So maybe let me shift this one to here, and then I want to write something. The function doesn't exist at y is equal to 0 for this particular function, for this matter graph, So the function doesn't touch the x-axis, So we don't have an x-intercept. Okay, with that being said, we know that our function doesn't exist where x is equal to 0. We get an error, and also our function doesn't exist where y is equal to 0. So our function will never touch those two values, of which are essentially your x and the y axis in this case, your x and the y axis, because where y is 0 is here, and also where x is 0 is also here at that point, So let's plot the points that we have with the functions that we have listed in the table. Okay, I forgot to put the values here. We're gonna have 1, 2, 3, 4, 1, 2, 3, 4, -1, -2, -3, -4, -1, -2, -3, -4. Okay, now let's plot the points. Where x is -2, y is -1. So it will be halfway. Where x is -2, y is -1. Sorry, I'm trying to say something if I made a mistake somewhere. Where x is -2, 1 divided by -2. Yeah, I'm making a mistake. So where x is -2, here y is -1. So it's gonna just be halfway there. We're gonna have a point here. That's the first point. And then where x is -1, y is what? Y is -1. So we're gonna have a point there, So I think it would have been nice to find what is the value of y where x is what? where x is negative half, where x is negative half. In fact, let me include that, because I think it's really gonna help us. Where x is negative 1 over 2, so we're gonna have 1 divided by negative half. That will be a negative half. Sorry, it's not, it's gonna be a negative 2. So 1 divided by a half divided by a half, it's gonna be a negative 2, and then let's add another value here. Let's add another value, and then we have 0 and error. Our function doesn't exist there. And then where x is 1 over 2, the y corresponding value will be 2. Okay, let's plot that point where x is negative half, sorry. Here our y will be negative 2. That's the third point. Yeah, I think that will be enough. And then let's go ahead. Then we have 0 and error. Our function doesn't exist where x is equal to 0. And then next we have 1 over 2 and 2. So we're gonna have a point here there just between 1 and 0, or halfway between 1 and 0. And then we have 1 and 1 here. We have 2 and half. Those are your points. Okay, so we've plotted the points, and then we have to connect the points now. And the way that we go about connecting the points is like this. So it is a curve, just like a parabola. This graph is a curve, just like a parabola. I'm trying to fit it here. Yes. Okay. And then let's also join the other points. Yes. Let's join the other points. So that is how you sketch a hyperbolic function. So what happens here is that our function will approach the y-axis, but it will never touch them. And also the function approaches the x-axis but never touches them, just like I have just sketched for you there. That is how you draw the function for those two values where x is equal to 0 and we have an error. Our function doesn't touch that area, and also where y is equal to 0, so we don't have x and y intercepts. So our function is now splitted into two branches. Maybe that's another characteristic that is worth noting, that a hyperbolic function has two branches. A hyperbolic, why did I separate this? A hyperbolic function has two branches, as you can see from the sketch there, So we have those lines or values that the function approaches but never touches. As I've already introduced to you and we have talked about a bit, we call those lines an asymptote. An asymptote, that is the line, or that is the weight for those values. So an asymptote is a horizontal line or a vertical line that the graph approaches but never touches. An asymptote is a horizontal line or a vertical line that the graph approaches but never touches. As you are seeing here, that's our function is approaching the x-axis but it never touches them. And also here on this branch, the function is approaching the x-axis but it never touches them. And the same goes for the y-axis, the function approaches them but never touches them. And that is your asymptotes. So the asymptotes are basically a horizontal and a vertical line because they only exist at one value. And you remember when we were doing the linear functions, the equation for horizontal and vertical line is just y is equal to n, and n is any real number. So in this case, let's in fact write the equations for the horizontal and the vertical asymptote. For the horizontal asymptote, the equation is y is equal to 0, and then for the vertical asymptote, x is equal to 0. We said x is equal to 0. That is your, sorry, y is equal to 0. That is your horizontal. That is your horizontal that is your horizontal asymptote. That is your horizontal asymptote. And then for x is equal to 0, that is your vertical asymptote. That is your vertical asymptote. Okay, so yeah, basically that's the matter graph of the hyperbolic function with the equation of y is equal to 1 over x. Now let's go ahead and deal with the general equation of the hyperbola. The general equation of the hyperbola, it is written as follows. So there are some changes that can be made to the matter graph of the hyperbola, essentially by changing the value of a and q. We can make some transformation to find different forms of the hyperbola, different forms of the hyperbola. Now let's quickly see what happens when we change the value of the variable a, this numerator there, the numerator. So a determines the vertical stretch of the branches from the x-axis. Remember, when we're doing the hyperbolas, that when we change the value of a, of which it was the coefficient of what? The coefficient of the x squared, our function got closer and closer to the y-axis. So what happens here when we change the value of a? When we change the value of a, the larger the a, the larger the stretch, the larger the stretch. And this is actually called a vertical stretch. The larger the vertical stretch, I can just say maybe a changes, let me do it like this, a changes the vertical stretch. So when we're talking about the vertical stretch, we're essentially talking about how far is our function from the x-axis. So when we increase the value of a, what we see happening is that our function maybe will be here. Now it is moving further and further away from the x-axis. That is your vertical stretch. But we're gonna do an example to show what we are talking about. So a changes the vertical stretch. So a determines the vertical stretch of the branches. How far are the branches gonna be? So the corresponding branch maybe will be here if we change the value of a. That is what happens. What happens when we change the value of a? The function is located a bit further from the x-axis. From the x-axis. That is a function with a increased vertical stretch. Okay, and also we can change the sign of the value of a, of that a. So when we have a negative sign, I think by now you should know that changing the negative sign simply do what? It reflects the function. It reflects the function about the x-axis. So if we were to change the sign of this matter function, so instead of having y is equal to 1 over x, which produced this function, we change it to what? Y is equal to negative 1 over x. You will see that you will end up having a function that is located now in these two quadrants, because they have been flipped about the x-axis. So negative sign of a reflects the function about the x-axis. Okay, and then next we have that q there on the general function, and the q that you see there determines the shift of the graph, upwards or downwards. So the q of the graph shifts the graph vertically. So just like we have witnessed with the two functions we have done already, that's when we add q, the function would move up. When we subtract q, the function will move down. The function will move down. So for instance, in this matter graph, if we were to say Now let's find the function of y is equal to 1 over x plus 2. That function will be shifted actually 2 units upward. It will be of this nature. It will be of this nature, and then you'd have an asymptote there. You'd have an asymptote there. Okay, but that is what it does. That q that you see here, it determines the vertical shift of the graph. It shifts the graph up or down. The q shifts the graph up or down. Okay, so hopefully you got that. It makes sense. Let's do some example, so that you can actually see what we are talking about. So example number 1. So the reason why we do this, examples, math is a practical subject and it needs you to practice, so that you can essentially develop the necessary skill and pattern recognition in order for you to be good at math, so you can't be lazy. Hence why we do a lot of examples. And after we are done with this introduction series, what we're gonna do next is more questions. So please stay tuned. So with example number 1, sketch the hyperbolas on the same set of x's. So a given array, we are given multiple functions, function number a, b, and c, and we are asked to sketch them on the same set of x's. And I want you to notice something here, that the value of a is changing and is becoming bigger and bigger with each function, so what are we expecting from what we know about the value of a? The larger the value of a, the larger the stretch. So we're expecting the function with the biggest value of a to be the most furthest away from the x-axis. But let's go ahead and sketch the functions. We'll select just a few x values. So let's select 2, -2, -1, -half, 0, 0, 1 over 2, 1, and 2. And let's just actually find the corresponding values for all of these functions before we start sketching. Then for a, corresponding y values for a, we have 1 over -2. That will be what? That will be -1 over 2. We have 1 over -1. That will be a -1. We have 1 over -half. That will be -2. We have 0. That will be error. That will be error. And then we have 1 over 2. That will be 2. 1 over 1 is 1, and 1 over 2 is 1 over 2. Okay, and then next we have the b function. Let's find the corresponding values that we're going to use to sketch the b function. So we have 2 over -2. That will be -1. That would be -1. We have 2 over -1. That would be -2. And we have 2 over -half. That will be -4. And then we have we have 2 over 0. Once again, we have an error. 1 over 2 over 2 over 1 over 2. That will be 4. We're going to have 2 here, and then we're going to have 1. And then for c, the corresponding y values, we have -4 over -2. That will be -2. We have 4 over -1. That will be -4. And then we have 4 over -half. That will be a -8. That will be a -8. And then we have an error. Then we have 8, 4, and 2. So those are the values for the third function. Okay, so once we have the values, now we have the points, we can go ahead and do the sketching. Let me make it a little bit bigger for this one, since the space allows. Let me see. We're gonna have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay, let's also calibrate the x-axis. We're gonna have 1, 2, 3, 4. In fact, we can use 1, 2, 3. Okay, 1, 2, 3, 4, 5, 6. So we'll calibrate the bottom scale using halves. Sorry, the x-axis using halves. So we're gonna have 1/2, 1, 1, and then it's 3/2, I believe. 1 plus is 3/2. Then we have 2, and then 2 plus 5/2. We have 3, yeah, and then we have -1/2, 1, -1, -3/2, -2, -5/2, and -3. And then here we're gonna have 1, 2, 3, 4, 5, 6, 7, 8. -1, -2, -3, -4, -5, -6, -7, -8. Okay, there we have it. Let's go ahead and start plotting our points for the first function of a. So function of a is basically the mother function, where x is -2, y is half, y is half. So here y is half, so that's the first point. It's gonna be there. And then where x is -1, y is -1, so it's here. And then where x is -half, y is 2, so somewhere there. And then we have 0 and error, it doesn't exist. And then next we have half and -2, so it's gonna be here, half and -2. And then we have 1 and 1, and then we have 2 and half, so somewhere there. And then yeah, we have our points. We have to sketch our function now. So this will be our function. Yeah, something of that nature. And then here let's also sketch our function. Okay, these are the points. So as you can see that the function approaches the x and the y axis, but it never touches them. Okay, so there we have it. Let's go to function number b and plot function number b. So where x is -2, y is -1, so it's here. Where x is -1, y is -2 here. And then where x is -half, y is -4 here. And then we have 0, and then we have where x is half, y is 4, so it's gonna be there. Where x is 1, y is 2, and then where x is 2, y is 1. So can you already spot that what we mentioned, that when we increase the value of a, our function moves further away from the asymptotes or the x-axis. As you can see here, that the function has now moved upwards, has been stretched upwards, and then it's still approaching the x-axis, but now it has been stretched. This is the corresponding function. Let's go ahead and increase the value of a to 4 now. A is the numerator for x, remember. So, and still, what are we expecting? We're expecting this function to even move much more further away from the x-axis. We are expecting the vertical stretch to increase once again. For C, we have, let's plot the function, let's plot the points. We have -2 and -2, so we're gonna have a point here. -1 and -4, we're gonna have a point here, and -0.5 and -8, -0.5 and -8. Okay, and then we have an error, that is our asymptotes. We have 0.5 and 8, 0.5 and 8. We have 1 and 4, 1 and 4, and then we have 2 and 2, 2 and 2. There we have it. We have the points. We have the points now, and that is the function. That is the function. We have the point. You draw the curve, you draw the branches of the function, the branches of the function. You see that even now the blue function, the function of y is equal to 4 over x, the function with the largest value of a, it is the one which is the furthest away from the x-axis, you know, from the x-axis. If we will just look at it, maybe if I'll just draw this, you see the vertical stretch, you know, you see it is the furthest away from the x-axis, you know, so the vertical stretch for the last function is much bigger, you know. So that what happens when you changes the value of a, the value of a there, you know. So a changes the vertical stretch. The larger the a, the larger the stretch, you know. So that is what you have there. That is what you have there. Now let's go ahead and sketch the following hyperbolas on the same set of axes. Example number 2. So here we are essentially investigating the effects of changing the value, the sign of a, you know. It's already introduced that changing the sign of a, what does it do? Changing the sign of a, it reflects negative sign of a reflects the function about the x-axis, Now let's go ahead and sketch these two functions and see what happened. We'll just let's start by selecting few x values that we're going to use to sketch this function. We're going to select -2, -1, -0.5, 0, 1, 2, we're starting with half, 1 and 2. Let's find the corresponding y values for the a function. -2, where x is -2, we're gonna have y over -2. Okay, so it's -0.5, -1, we're gonna have -2. We have an error. We have 2, 1 and half. Let's find the corresponding values for b. We have -1 over -2, -1 over -2. That is gonna be a positive half, just 1 over 2, and then -1 over -1 is just gonna be 1. -1 over -half is just gonna be 2. We have an error there at 0. We can't divide by, so it's essentially undefined. You can either write an error or undefined, and then we have -1 over -2. Now we get a -2. 1 over -1 is -1, and then 1 over -2 is gonna be a -half. So those are your values. Let's go ahead and plot these two functions. Let's calibrate our x and y values. 1, 2, 3, 4. 1, 2, 3 and 4. So it's 1, 2, 3 and 4. It's 1, -2, -3, -4. 1, 2, 3, 4, 1, -2, -3, -4. Okay, let's plot the points. Where x is -2, we have -half, so it's just halfway there. Just plot halfway there. Oh, sorry, it's -half, so it's gonna be below, right about there. And -1 and -1, it's gonna be here, and -half and 2, so it's gonna be here. Remember, this is just about halfway there. And then the other branch, it has 2, half and -2, sorry, half and 2. This is the coordinates I'm referring to. I keep on missing this thing, messing up since it's the negatives and stuff. So 1 and 1 and 2 and half, 2 and half. And let's join our branches. Let's connect our points. That one doesn't fit very nicely. Don't know why it doesn't fit. Okay, but yeah, you get the point. So those are your 2 branches. And then next, now let's sketch the negative function of -1 and x, -1 and x, and see what happens. So what are we expecting? We're expecting, since these functions are basically the same, just differs in sign, we're just expecting one function to be reflected about the x-axis. Let's see, what do we get? Where x is -2, half, sorry, yes, y is -half, y on b now. And then we have -1 and 1 here, and then we have half and -half and 2, so about there. And then we have -2 and, oh sorry, half and -2, and then we have 1 and -1 here, and then we have 2 and -half somewhere there. Let's join our points to form our branches. Now would you look at that? These are exactly the same set of functions, just that the other one has been reflected about the x-axis, and that is what happens when you change the value of a, because this y is equal to 1 over -1 over x is the same as y is equal to -1 over x. It's the same thing, it's the same thing. Okay, so that was example 2. Once again, we said negative sign of a reflects the function about the x-axis, of which is what we see happening here. This function here, original function, has been reflected about the x-axis. So just imagine if you were to place a mirror here on the x-axis, this function will be mirrored below as this function, as we are seeing there, and then this function will be mirrored upward by that function. So changing the sign of a essentially reflects the function about the x-axis. Hopefully you do get that point. Let's go ahead and do example number 3. Sketch the following hyperbolas on the same sets of axes. Okay, what are we seeing here is that we start with y is equal to 1 over x, and then for the second function we add a value of 1, so that is adding what? A q, and then we add a value of 2. What are we expecting here? What have you said about the value of q is that q shifts the function up or down. It shifts the function, and it also shifts what now? It shifts the asymptotes. It shifts the horizontal asymptotes, by the way. It shifts the horizontal asymptotes. Okay, let's go ahead and sketch these functions, So when we are saying it shifts the horizontal asymptotes, remember that for the matter function, the asymptotes were these. The asymptotes for the function of a, the asymptote. What's the equation of the asymptote? We said it's y is equal to 0 because it doesn't have an asymptote. That's the matter function. When we have y is equal to 1 over x, the asymptote is always going to be y is equal to 0. So here, when you were to be asked to find to determine the asymptote of the b function, you just take it as y is equal to 1. That's your horizontal asymptote. And then for the function of c, the asymptote will be y is equal to 2 now. Y is equal to 2 now. Okay. And that is your asymptote. Okay. What else did I want to mention? And you'll also see that now our function will have an x-intercept because the y now touches the function will now touches the x-intercepts because the asymptote has been shifted. Okay, but let's just sketch this functions. Hopefully we'll be able to see what I'm talking about. Let's start with our table. Our table. So it's x values. Let's see, x -2, -1, -half, 0, 1 over 2, 1 and 2. Let's find the corresponding values for a, the function of a. So y corresponding values is -1 over 2, -1, -2, 0, it's undefined, it's not 0, and then we have 2 and 1 over 2. Then for b, let's find the corresponding y values for the function of b is y over 1 over x. So it's -half plus 1. That will be just a positive half. And then we have -1 plus 1 is 0. And then we have -2 plus 1 is -1. And then what else do we have here? Where x is equal to 0, it's still undefined. And then we have 1 because we're gonna have what? 2 plus 1. No, it's not 1. So I'm making a mistake. 2 plus 1. Let's punch in the calculator. Y over 1 over 2 is 2 plus 1. It's gonna be 3. 1 plus 1 is gonna be 2 here, I would like to believe, and then it's gonna be 1.5. So we're gonna have 1 over 2 plus 1 is 3 over 2, which is 1.5. 3 over 2. It's 3 over 2. Okay. We still have the c function now, which has been shifted 2 units upwards. We have -half plus 2. Let's punch that one. -half plus 2 is 3 over 2. And then we have -1 plus 2. -1 plus 2 is gonna be 1. We have -2 plus 2 will be 0. We have your undefined there. We can't divide by x. And then we have 2 plus 2 will be 4. 1 plus 2 will be 3, and half plus 2. It's 5 over 2. So those are the corresponding values for the c function. Let's go ahead and sketch these 3 functions now. Let's go ahead and sketch these 3 functions. Start by drawing your Cartesian plane. Have 1 2 3 4 5. 1 2 3 4 5. 1 2 3 4 5. 1 2 3 4 5. But we'll just use the half. So we have 1 2 3 4 5, -1, -2, -3, -4, -5. And here let's use the halves. 1 over 2, 1, 3 over 2, 2. then we have negative 1 over 2, 1, negative 3 over 2, negative 2. Okay, let's plot the corresponding values. So for the first function, it's just the parent function where x is negative 2, y is negative half, so it's just about halfway there. Where x is negative 1, y is negative 1, so it's going to be here. Where x is negative half, y is negative 2, so it's just there. And then we have undefined, and then we have 1 over 2 and 2. There we have 1 and 1. There we have 2 and half. There, that is our function. You join the points, then the other function, and there you have your first function. Let's go ahead and sketch the second one. Negative 2 corresponds with half. What did we say was the asymptote now? For the second function, the green one, the asymptote is y is equal to 1. It is always best to start by just plotting that asymptote, before we start sketching, so that we know the asymptote will be here at y is equal to 1. That's the asymptote. Can just use this dotted line to show that's the asymptote, y is equal to 1 for the second function. Then we can plot the point. So we know that the function, the y value that the function doesn't exist at is y is equal to 1. Okay, let's plot the function. We have negative 2 and 1 over 2, so it's going to be here negative 2 and 1 over 2, and then we have negative 1 and 0 is there. We have what is this thing, negative half and negative 1 is there, and then at 0 it's undefined. And then let's go ahead and have where x is where x is 1 over 2, here y is 3, so it's going to be there. That's the point. At 1 and 2, at 2 and 3 over 2. At 2 it's 3 over 2, so it's basically 1.5, so it's going to be here. And then once you are there, you have to sketch your function. Function will be like this. It approaches the the y-axis, but it never touches them. That's your asymptote. Just as I can continue. There you have it. And here that is the red line is the asymptote. The function cannot touch the asymptote. It approaches the asymptote, but it doesn't touch it. And you see what happens here. We said by adding that 1 here, we're expecting the function to shift 1 unit upward, and we are seeing that the function has shifted upwards, by 1 unit. When you go back to the original function, where x was negative 1, y was what? Y was negative 1 in this original function. So it has been shifted 1 unit upwards. So we add 1 unit. We expect the other function to go up from negative 1 by 1 unit. So we say negative 1 plus 1 is going to be 0. That's why we have this point here. So this function has been shifted upwards. The function has been shifted upwards, just like that. And then next we have the c function. It has an asymptote at what? At y is equal to 2. So it doesn't touch that point. Let me use, so it's a blue function. Let me use this color to represent the asymptote. So it's at y. It's not as clear. Let's see, maybe this one would be better. Still the same. Which one? Let me just use 3. So for the third function, our asymptote now has moved to y is equal to 2. has moved to 2, y is equal to 2, because our function has been shifted 2 units upwards. 2 units upwards. Let's go ahead and sketch the coordinates that we have, where x is equal to negative 2, y is equal to 3 over 2, which is 1.5. So negative 2 and 1.5 would be there, and then will be there, and then we have where it's negative 1 and 1, it's right there, negative 1 and 1. Hopefully you are paying attention that this is the asymptote here, not the other one, not the red one. Okay, and then we have half and 0, negative half and 0, negative half and 0, and then we approach the y-axis but never touches them. The other points are what? Half and 4, half and 4. So the other point will be here. It's half and 4, and then we have 1 and 3. 1 and 3, and then we have 2 and 5 over 2, which is 2.5. So it's gonna be there, and then we sketch our function. Making a mistake. It approaches that green line but it never touches it. Approaches that green line but never touches it. The same goes for here. That is our function there. That is our function, and you see it has been shifted upward. It has been shifted upward with 2 units. 2 units. So you can see that changing the value of q shifts the function upward. Okay, so next we have example 4. So for example 4, for number 1, we are asked to describe the transformation from y is equal to 4 over x. What are we seeing here in this function that we have been given? That it has a negative. So that function means what? The function has been reflected about the x-axis, and then we have a minus 1. Those are the 2 transformations they've done to move the y is equal to 4 over x to this function. Now let's put what I've just said in words. So for number 1 there, y is equal to 4 over x. Function has been reflected, that negative there, reflected about the x-axis, and then we subtracted 1 and shifted 1 unit. When we are subtracting, we are shifting down 1 unit downwards. Okay, and then algebraically determine, for number 2, algebraically determine the x-intercepts of this graph. To find the x-intercepts, what do? We have to equate. To find x-intercept, we have to equate y to 0 intercept. And remember that a function that has a value of q, that has a q, whether it's subtraction or addition, does cut the x-axis. Hence why we have the x-intercept. So to find the x-intercept, we have to equate y to 0. To find x-intercept, let y equal to 0, and then we just solve for x from there. Y is equal to 0. So our function is y is equal to negative 4 over x minus 1. We equate y to 0. This is equal to negative 4 over x minus 1. Put the 1 on the other side. We're going to have 1 equal to negative 4 over x, and therefore x is equal to negative 4. That is your x-intercept. And then next we are asked to sketch the graph of y is equal to negative 4 over x minus 1, clearly showing the x-intercepts and the asymptotes. Okay, let me add the page. Let me add a page. 8. Okay, we are now asked to sketch the graph. Okay, to sketch the graph and clearly show the x-intercepts. Okay, let's come here. Before we even do the table, there are certain things we can just do from the word go. Okay, I'm seeing what calibration should I use. Let me see. If we say 1 2 3 4, oh, we do have a space actually, so I can make this one a little bit bigger. Yeah, okay, calibration. This is our x and y axis. X and y axis. We have 1 2 3 4 5 6 7 8. Let's use the halves here. Negative half, negative 1, negative 3 over 2, negative 2, 1 2, negative 3, negative 4, negative 5, negative 6, negative 8. We have 1 over 2, 1, 3 over 2, and 2. We have already calculated the x-intercepts, which is y is equal to 0, and the asymptote. I said we can just read it from the equation here, which is negative 1 over 2. We take it with the sign. So the asymptote is y is equal to negative 1. Y is equal to negative 1. Y is equal to negative 1. That is the, what you call this thing there, horizontal asymptote. Horizontal asymptote. And for the vertical asymptote, it's still x is equal to 0. X is equal to 0. That is your vertical asymptote. That is your vertical asymptote. So the vertical asymptote is just x is equal to 0, so it's this one, and the horizontal asymptote is negative 1. Let's plot. Let's show the line for the the horizontal asymptote is this one of y is equal to negative 1. That's your horizontal asymptote. Our function, we expect our function to approach this line but never touch it. And that function is negative, so it has been reflected, so since it's negative, we are expecting it to be this side and this side. But let's just do the table, for the completeness sake. Let's do the table to find the corresponding values. Let's pick our x values. We're going to have negative 2, negative 1, negative half, 0, 1 over 2, 1 and 2. The corresponding y values, we're going to have negative 4 divided by negative 2 is just going to be 2 minus 1 is 1. Negative 4 divided by negative 1 is 4 minus 1. This would be 3. And then we'll have 8 minus 1 is 7. 0 is undefined. And then we have negative 4 divided by x divided by 1 over 2. That would be negative 8 is negative 9. And then we have negative 4 divided by 1 is minus 4 minus, it's minus 5. And minus 4 divided by 2 is minus 2, it's minus 3. Those are our values. Let's plot the points. We have negative 2 and 1. Negative 2 and 1 here. Negative 2 and 1. And then we have negative 1 and 3. We have negative 1 and 3 here. Negative 1 and 3. Then we have what do we have next? Negative half and 7. Negative half and 7, so it's about there. And then next we have, for the other branch, we have negative half and negative 9, so it's about there. Negative half and negative 9 will be here, negative 9. And then the next point we have negative 5 and 1 and negative 5, so it's about here. And then we have 2 and negative 3, 2 and negative 3. So those are our points. What do we do next? We join our points, and that is the function as you see. Okay, as you see it, and that is our function. That is our function. And the function looks like that, with the horizontal asymptote being y is equal to -1 and the vertical asymptote being x is equal to 0. Okay, yeah, so we're done with this question. Let's go to example number 5. Example number 5. So you are given y is equal to -3 over x plus 2. X plus 2. Okay, so we asked to write down the equations of the asymptotes. So for number one, the equations of the asymptotes, I said for the horizontal asymptote, you simply read it here. It's y is equal to 2. Y is equal to 2. That is your horizontal asymptote. And then we have x is equal to 0 for the vertical asymptote. And then next we are asked to determine the coordinates of the x-intercept, so we're just gonna find it algebraically. So for x-intercept, let y equal to 0. That's how we solve for the x-intercepts. Our equation is y is equal to -3 over x plus 2. Okay, and then we equate y to 0. We're going to have -3 over x plus 2. Let's solve for x. We put the 2 on the other side. We're going to have a -2 is equal to -3 over x. Therefore x is equal to 3 over 2. The negative and the negative will cancel, but here we are looking for the coordinates, so the coordinates are going to be 3 over 2 and 0. 3 over 2 and 0. And then for number 3, we're asked to sketch the graph on the set of axes. Yeah, let's just do the table and sketch our graph. Let's do the table and sketch our graph. We have x. For the x values, we're gonna go with -2 and -1, 0. Since we already have those 3 over 2 there, let's just go with 1 and 2. Let's find the corresponding y values. Corresponding y values are gonna be -2. Okay, let's find the corresponding y values. It's -3 over -2 plus 2 gives us 7 over 2, which is like 3.5. 7 over 2, and then we have -3 over -1. -1 plus 2, we get 5. Then we have 0, we get undefined. 0 gets undefined, and then we have 1 negative 3 plus 2 is negative 1. I think it's negative 3 over 1. Negative 3 plus 2, yes, it's 1. And then for 2 we have negative 3 over 2 plus 2, which is half, gives us half. Okay, negative 3 over, yeah, so those are the values. Let me add a page so we can sketch this function. Add a page, custom, create. Okay, now let's sketch the function. Let's quickly sketch our function. We have 1 2 1 2. This is 1 2, negative 1 negative 2. Then we have 2 4 6. Do we have 7s there? 2 4 6. I think to be enough. 2 4 6. We have 2 4 6, negative 2 negative 4 negative 6. Let's plot our asymptotes. Asymptotes is the y asymptotes, or the horizontal asymptotes is y is equal to 2. So this is the line, our function that will never touch. That's the asymptote, and we can just sketch the function. So we have those points there. Those points where is negative 2 and 7 and 7.7 over 2. Negative 2, where is negative 2? It goes with 7 over 2. 7 over 2 is like 3.5 divided by 2. Let me see. Yes, it's 3.5. So 2 negative 2 goes with 3.5. 3 is about there, so 3.5 is there. 3.5. So 2 goes with 3.5. So we're gonna have a point there. And then we have negative 1 and 5. Negative 1 and 5. 5 is there between 4 and 6. And then we have what do we have next? 0 is undefined. Then we jump to the other branch. We have negative 1, and we have 1 and negative 1, so it's here, 1 and negative 1. And then we have 2 and half. 2 and half will be here. Remember that the x-intercepts is 1.5, so it's here. That's your x-intercepts. And then from there you simply just join your points. Join your points. Just like that. Yes, the asymptote is y is equal to 2. Our function will approach that line, on both directions, but it will never touch this line as it is approaching the y-axis but never touching them. That's how you'll go about answering example number 5. Okay, so that is that for today. I will see you on the next video when we are doing exponential functions. Until we meet again, I wish you good luck and good studying.